All right, so I'm also going to be talking about the center of our galaxy, and I'm actually toward the end here going to try to start making comparisons with the center of another galaxy. Now, almost everything in this talk, I've been very, very careful to put things to scale in size. This slide is an exception because I'm lazy. So here, of course, one problem is these galaxy sizes are not to scale, and of course, they're not that close in the sky. Because one of them we live inside, and so the other problem here, of course, is we live inside this galaxy. We never can have this view of our own galaxy. So living inside of the galaxy, we are about 8 kiloparsecs, give or take, from the very central regions of our galaxy. And because of that, looking toward the center of our galaxy, you have to look through the disk of our galaxy to get to the very center. And this limits also the wavelengths that you use. So if you're trying to use optical wavelengths and look toward the center of our galaxy, you will essentially see a whole lot of nothing. So as I zoom in here, I'm going to be zooming in not just in size, but also going to longer wavelengths. So going to infrared wavelengths, where now you're piercing through most of the dust, and you can actually see that the center of our galaxy is a concentration of stars, hot gas, hot dust, right? A lot of activity. And zooming in further to the region that I want to talk about, the central molecular zone, around 300 parsecs end to end. And what you're seeing here is a 3-color composite, where the orange now is showing you the cold gas and dust. So each of those blobs is a giant molecular cloud and has something like 100,000 to 1 million solar masses of gas inside it. And of course, this is living in an environment of stars and clusters that have already formed, some of which are traced by the infrared in green, and some of which also are ionizing the gas, so making the purple emission, as well as various non-thermal emission, coming, for example, from the very center of our galaxy, around the supermassive black hole, Sagittarius star. So what I want to do now is start with a little bit of an accretion journey, because one of the things we're interested in, as was just mentioned by Robin, right, is how gas makes it into the center. So I want to give you an idea of just how long this journey is and the sort of scales you have to go through. So now I've switched back into right ascension declination, and we're going to be zooming in again toward the center, so toward the very central black hole. So the first step here is just a nice radio image. And so we're seeing, okay, there's a supernova remnant here. There may be a few forming stars in compact H2 regions, but the real activity is where the cross is. This is centered on our central supermassive black hole, Sagittarius star. So the next zoom gives you basically the stopping point right now for molecular gas. This is about as far in as this whole molecular gas reservoir. So the central molecular zone has maybe 10 million solar masses worth of gas. And about 10,000 solar masses of gas make it into this structure called the circumnuclear disk. So this is gas that's about, gas and dust, about a parsec away from the supermassive black hole. All right, everything beyond this, you're starting to look at gas that is either neutral or ionized. And you start seeing this, particularly this very, very hot dust here. So this is a forecast dust image. The hot dust is tracing a structure known as the mini-spiral. So you also see this in ionized gas. And so this is gas that's starting to make it a little bit closer to the black hole. A lot less of it, though. So even though that dust is very, very bright, the amount of gas that we believe is here in these ionized gas streams is about 30 solar masses. So you're talking about much, much smaller amounts of gas. Maybe as much as 300 solar masses in the neutral gas, neutral gas inside of the circumnuclear disk, but not much. So as you go in further, now you start being dominated by stars. So you get into the central light year here. And one more zoom takes you into now the stars that are used to determine the mass and tell us that there is a central supermassive black hole. And so these stars are about 0.03 parsecs away from the black hole. And they're so close to it, of course, that you can actually see their motion. As you watch them for dozens of years, you can actually see them going around. Now, one last zoom just for fun, because of course this is something we're all waiting for eagerly. But you might want to ask, okay, so the gas has made it this far. How far does it have to go to actually get to the supermassive black hole? So the type of simulation of what we hope to see soon from the Event Horizon Telescope, note that this is, we've gone from 0.03 parsecs for the star cluster down to that 6 zeros, 0.0000002 parsecs, right? So an extreme journey, many orders of magnitude that the gas has to take. And one of the things that's most interesting, right, is asking exactly how far does this gas go, for example, to do things like form stars. So everyone's here for the star formation, so I want to give a little sidebar. Where is the star formation happening on all of these scales, right? So is it forming stars? Where are those stars? So the first scale that I want to talk about is the very center here. So this is Sagittarius B2. This is about 100 parsecs away from the black hole? And here the answer is yes, thumbs up. It is forming stars. In fact, presently we believe. So we see hot cores, for example. So this is an example of, yes, we are forming stars. You can go a little bit closer to the supermassive black hole. Now we're maybe 30 to 40 parsecs away. Now, of course, we don't know exactly where they formed. And you see clusters that formed anywhere from 3 to 6 million years ago, right? Very massive star clusters. So we see evidence of past star formation. And then we ask, okay, now when we're zooming in, what else do we see? So if we zoom into 7 parsec scales, as I noted before, we see these sort of compact H2 regions. So this is nice. This looks like maybe star formation within the past, say, 100,000 years. Just one problem. If you believe current models, for example, from Dietrich Croysen, even though these look like they're maybe a few parsecs away from the black hole, current models actually put these as much as 50 parsecs in front of the black hole. So that's recent star formation, but it's not actually star formation that close to the black hole. You can go a little bit further and ask, is the circumnuclear disk forming stars? I will just say no, right? There's some controversy here, but at this point, our best evidence for how dense the gas is and things that unambiguously trace star formation suggest that there is not active star formation in this structure. And you can keep on zooming in a little bit. Definitely no, right? There's really not enough gas in the mini-spiral, and it's all ionized and neutral, so we don't really think that that's forming stars. And then we get to another yes, but again, a long time ago. So the S stars, for example. These are interesting because we believe they formed actually where they are right now, right? Only 0.03, 0.05 parsecs away from the black hole. And so this cluster actually shows that you actually have to you can take gas all the way that far in, right? And form stars, even though at this point, right, this is as far as we've gotten stars right now. Of course, you can ask, no star formation there. Focusing on those S stars, because they are really interesting, the central nuclear young cluster here. This is the only clear evidence that we have in the galactic center of star formation actually being weird, because maybe the conditions themselves are, in fact, as we know, the gas conditions are quite weird. So here, again, the stars that formed 0.03 parsecs away from the black hole, here you actually see evidence for a top-heavy IMF. And the reason I say this is our best evidence right now is because these stars mostly formed in the potential of a supermassive black hole, and for the most part likely stayed there. Whereas when we measure the IMF, or rather the present-day mass function of the other clusters, it's very likely that they've been stripped significantly by their journey throughout the central potential. So here we say, okay, stars that close to the black hole seem to have formed differently. So one question is why? And of course, sort of qualitatively, I'll say, okay, you're really close to a black hole, things are going to be freaking weird, but what exactly is going on? So in general, in the galactic center, the gas is at least one order of magnitude more extreme than we see elsewhere in the galaxy. So it's about an order of magnitude hotter, up to 200 Kelvin, compared to the sort of 10 to 20 Kelvin you see in the gas elsewhere in the disk of our galaxy. Also, on average, much more dense because it is packed into a very small region. So you've got average densities, about 10 to the 4th molecules per centimeter cubed. Average densities in the disk, about 100 molecules per centimeter cubed. And then, of course, it is much more turbulent. So on these sort of cloud scales, you see line widths 10 plus kilometers per second, where you might see a few, and other infrared dark clouds. And so one question is, okay, this is plenty weird, but we don't yet have evidence that this amount of weirdness forms stars with a differing IMF. What happens as you actually go close in? So now as we go as close in as the circumnuclear disk, do we actually start seeing evidence that the gas is significantly more extreme, perhaps in a way that would help us to understand how much more extreme the stars are that formed closer? So to do this now, so this is work with an old telescope, so you have to go back in the day a little bit. So this is the ISO satellite doing far infrared observations, because these are observations actually of H2, molecular hydrogen. The thing that we all want to know what it's doing, but in most environments, they're too cold for us to actually see substantial emission directly from rotational lines of H2. Nice thing about the galactic center, it's hot, right? So here you actually get a significant population in these H2 lines. And so here I'm showing you isospectra in these boxes toward 3 positions of the C and D. These are spectra of pure rotational H2 towards the southern region. We don't detect the S0 line, the lowest line, but we make up for it by detecting everything up to S13. So very highly excited lines of pure rotationally excited hydrogen. And you can use this to measure the temperature of the gas and also measure the mass of the gas, but that's another story. So focusing on the temperature, so you can count up, right, the number of molecules that you see in each of those different energy transitions, plot the column density, here normalized, against the energy of that transition. It's called a Boltzmann plot, and it lets you know something about the temperature of the gas. If there's a straight line on this plot, generally that tells you single temperature component. Curvature, you start to ask yourself, okay, are there actually multiple temperatures present? What we did is we said, okay, we see curvature, and we actually want to describe this maybe a little more physically than has been done, not by saying there are 1 or 2 temperature components, but a continuum of temperatures. So what we do is we fit this with a power law where we essentially say that at each temperature, there's an amount of gas at that temperature proportional to the temperature to some exponent, right? So T to the minus N. So that power law exponent, what that tells you, if N is small, that means you have a flat slope. More gas at high temperatures relative to low, compared to a steep N or a large N, in which case you have less gas at high temperatures compared to low. And what's interesting is we see very clearly toward the circumnuclear disk a power law index of about 2.8 that's significantly lower than the power law index you see toward other galactic center molecular clouds. So we see evidence that in this gas that's within a parsec away from the black hole, you actually see temperatures that are much more hot gas relative to the amount of cool gas. So elevated temperatures. So you can ask why, right? So what's going on that's making this gas hotter? So this gas doesn't seem to be radially excited. It seems to be collisionally excited. Another interesting thing going on is the line widths in the circumnuclear disk are very broad compared to other regions in the galactic center. And so there's been nice work, for example, by Katha Immer, who's been showing that there seems to be a correlation between line width and temperature in the galactic center, suggesting that turbulence is the number one thing doing the heating. And so what we're saying here is this seems to be starting to tell us a story where as gas gets further into the center of the galaxy, it gets more turbulent and it gets hotter, right? And if you're seeing this sort of radial dependence, that maybe suggests that actually the fundamental place that this energy and the turbulent energy is coming from is actually from gas just falling into the potential of our galaxy. Because our black hole is not an AGN, and there's not much star formation going on in our galaxy. There's not much in the galactic center. There's not much that would be causing feedback type processes or other things that might be heating. This seems to be sort of a passive heating where it's a story of just getting gas to the center of a galaxy already uniquely changes it compared to the rest of the galaxy. So now we want to ask, okay, so that was our galactic center, super nice case study, right? Really close by, really easy to see what's going on in detail. Now you want to start comparing it to more extreme things. You want to have a sample size larger than 1 to look at galaxies where maybe actually something, anything is happening, right? So one option is NGC 253. It's about 3.5 megaparsecs away. It also does not seem to have an AGN, but what it does have is a nuclear starburst. So it does have in the central regions about an order of magnitude more gas, and about an order of magnitude higher star formation, at least. So it's producing something like 3 solar masses a year, whereas our galaxy is producing maybe less than 0.1, right? So not much star formation. So this is a nuclear starburst, and so we want to ask now, how are conditions changing here, right? How are conditions changing relative to sort of the baseline that we've established for the center of our galaxy? So this is all a work in progress, but I want to show you some of the nice new ALMA data here. So first, again, we have to always zoom in. So zoom in on the nucleus of the galaxy. So here's a Hubble view now. Zooming in a little bit further, you can start to see the central starburst, actually just at optical and infrared wavelengths. So you can see each of those dots is now a super star cluster, essentially, that is forming there. And you're starting to see, okay, so this black bar is about half the size of our central molecular zone. So we can zoom in on this and examine the starburst in really nice gory detail. But now, of course, what we want to know is where is the gas, right? Where is the fuel for this starburst? Where is it located? So these are ALMA images from working with Alberto Bellato and Adam Leroy. So these are our new long baseline. This is band 7, so HCN 4 to 3. And here we're getting down to spatial scales of about 2 parsecs. So about 2 parsec spatial resolution, looking at what the gas is doing here. So we can compare this to a really nice map that was made by Kunihiko Tanaka. Exact same line, slightly higher resolution in the center of our galaxy. And we can actually start making what I'm really excited about, which is this apples to apples comparison, right? Same lines, same resolution, same region, and start asking what's going on. Already you can see one of the big differences in the black contours here, which are radio continuum, which is that here, it's a starburst, as we expect, right? Basically every cloud here has a forming, likely, cluster slash supercluster going on inside of it, right? So almost every cloud here really appears like it is forming stars like gangbusters. Whereas here, basically the only place that would be happening is Sag B2. One of the really nice things when you start to ask what is actually setting, right, the scales of everything happening, is to look not just at the size scale, which again is a gorgeous match, but also at the velocity structure of these two. And so here you can see, so here's sort of the same sort of image of the same size scale, but now I'm showing you a position velocity plot. And again, in both of these, NGC 253 is also a barred galaxy. You see a nice tilt here and also a separation in the velocity, which is suggesting, again, the same sort of ring or stream features that are going on. Main difference that we see so far is certainly a broader line width in NGC 253. But we've not looked carefully to see to what extent that's a broader line width in the few clouds that are not as actively star forming, and to what extent this is actually a broader line width because something, potentially these clusters, is in fact launching a molecular wind from the disk of NGC 253. So going forward, so what we're really interested in, two things, again, really sort of understanding how the center of our galaxy, what sets the conditions here, and to what extent this is a nice example of initial conditions without feedback effects. So gas is extreme simply by virtue of getting the journey, getting to the center of the galaxy, and not necessarily because of what it encounters there. And then using this to start make really nice comparisons and start isolating, right, now just the effects of feedback. So again, a nice sample that says we're still not worrying about AGN, but starting to understand just how stars and stellar feedback are now changing the gas properties in addition to what we find in the center of our galaxy. Thank you.
For a couple of quick questions.
Yeah, this is very interesting to do this kind of comparison. It should be done for more galaxies, I think. One question I had is you said that 253 was a starburst, yet 2.8 solar masses per year is kind of low for what I thought a starburst was. Is that only from the nuclear?
Exactly, yes, so apologies. So that is specifically for the inner, I think, around kiloparsec, so the nuclear starburst.
How does that compare to the overall star?
That I don't know. I believe that the center is much more active than the rest of the galaxy, but I don't know exactly what the rest of the galaxy contributes.
Sandra, you can set up.
If someone else has a question, I just wanted to ask, I don't know what HCN trace is.
Good question. Mean question. Yeah, so I mean, nominally HCN traces somewhat denser gas than you see with CO. But in general, it's found pretty ubiquitously, as in our paper, even at relatively low columns toward the galactic center. So it seems to be quite extended. So in general, it seems to be a pretty good tracer of just gas that is in the galactic center, not necessarily the densest gas that is in the galactic center.